right. Thank you very much. Thank you very much for your kind invitation, guys. I mean, I would have preferred to be actually there, like physically there, but you know, virtually is also will do. Let's say at least at the moment. So yes, let me share my screen. I don't know if you can see it. Can you see it now? I guess so.
Yes, we can see it.
All right. So as Alexi was saying, this is a talk that is centered mostly on retrieval augmented generation. We'll go over that let's say stuff in a moment, but before that, I would like to actually you know, share with you some historical notes and why we're actually interested in those problems. So we can say that everything, you know, revolves around the tale of two index types. I mean, in the literature, historically, we had two main, let's say, ways of searching. Mainly, let's say, in the case of text, the main data structure was, let's say, the inverted index. I mean, the picture is shown here on the left-hand side of the slide. And when you actually have to search through objects that can be embedded into a metric space, then there has been like a lot of different data structures like KD3, M3, Quad3. I mean, everything has been done in order to speed up the search procedure. Of course, I mean, in both cases, you can do an exhaustive search, but without an index, right? But that would cost you a lot of time. Of course, if you have to do, for instance, a grep into a textual file, you don't need to build an index first because you only want to run the search once. So building an index would cost a lot of time. But in general, this was what we were doing, right? And this was actually, in particular, the inverted index was the king or the queen of the web search space. So when dealing with text and web pages in particular, the inverted index and some modifications of it were, let's say, was the main actor. So here you can see a very, very, let's say, high-level architecture of a search engine like Google. And as you can see, after you crawl the page, you build a page repository, and at that point, you build an index that would allow the query engine here to actually process your queries in a very, very fast way. So that's the reason why when you go to Google and you search for something, you know, it looks magical. It says, let's say, it looks like immediate, right? The problem, I mean, through time, this paradigm has shown many issues, right? And in particular, in the last years, let's say, people realize, I mean, this has always been a problem, but this has become a main issue given that people have become more and more experts searching, you know, the web. And so there is the problem of query ambiguities. So queries are ambiguous by definition. If I say, for instance, if I search for the query tree, what do I mean? Do I mean let's say, the tree in the forest? Do I mean a data structure? You know, do I mean like, I don't know, a hierarchy, whatever? So searching is a ambiguous problem by definition. And there's been many, I would say, techniques that have been developed and let's say, and also features that have been developed to deal with the concept of query ambiguity. For instance, in this case, there is these people also search for, let's say, panel in Google search that helps you refining or moving around, let's say, in the search space, the query that you entered. So for instance, in this case, you search for query ambiguity, and maybe you wanted to know the meaning, or you wanted to see some examples, or you wanted to see some types of search queries, etc., etc. So in the past and throughout the time, people have tried to deal with query ambiguity. Meanwhile, in the natural language processing, which has always been a sort of a cousin, right, of information retrieval and web search, people started to kind of think about how one could use, let's say, the modern methodology, methodologies and models that deep learning and deep learning, let's say, technologies were developing, right? So I'm sure you know the major success of deep learning came from images. So deep learning techniques were able to kind of take, let's say, the ImageNet competition by storm. Like until the very first deep learning methodology, the improvements in the error rate decay were in the order of 0.5, 0.3% of error points. When deep learning methodologies were discovered or were proposed, the error went down a lot. Now, the problem is that, let's say, since the beginning of the deep learning revolution and until the time when this deep learning revolution also kind of took the natural language processing community, we were thinking that maybe deep learning was not the right thing for NLP. And in particular, one of the things that were kind of envied to the computer vision community was the fact that you can pre-train a deep learning model on some self-supervised tasks, like like ResNet and stuff like that. And once you have pre-trained a model, you can then use this pre-trained model on different tasks. I mean, with a methodology known as fine-tuning, right? So you take your pre-trained model, you take your new task, and you fine-tune the model to the new task. And this was working beautifully. So essentially, we kind of found the holy grail of computer vision models, right? But not for NLP until like models like Elmo or BERT, and that's the reason why there is this recurring joke of the Sesame Street. Those are some characters of Sesame Street, so Elmo, BERT, Bart, etc. So until then, we didn't have any real revolution. But then Elmo, and subsequently, like almost at the same time, this model here that you can see, and this was 2017 at NIPS, but back then the conference was called NIPS, now is New RIPS. There was this much celebrated paper, Attention is All You Need, that I believe has reached more than 130,000 citations up to now. And this paper came out and essentially showed that you can indeed encode your data only using this mechanism that is called attention. I will not go into the detail, but essentially the idea there is that you can understand the meaning of a word by looking at the representations of the words surrounding it. Okay? Now, this was not a very new idea, meaning Word2Vec, which was another celebrated paper or another celebrated technique, it has won the Test of Time Award, that paper at the recent New RIPS in 2023. So Word2Vec was doing the same, except once it had computed the representation, so in particular, the representation of word is a vector in a vector space. Once Word2Vec had computed the representation of a word, that was it. So, for instance, the representation of tree was one and only one, not different. So it was not. So the representation was not changing depending on the context it was used. It was a static embedding. Indeed, after the 2017 paper by Google guys and Google Brain guys, the Attention is All You Need paper, in 2018, there was, let's say, a series of papers. Elmo was first, and then BERT, that showed that finally, using this kind of contextualized word embeddings, and the difference is that the representation of a word is not statically computed at the beginning, but can be computed on the fly. Of course, you pre-train a model, and then you use this pre-trained model to extract the contextual word embeddings. And then with those contextual word embeddings, you can use, you can train, downstream models. And so, if you look at the performance of BERT or Elmo and all the subsequent, transformer-based models, and those, led then to the revolution that we are experiencing nowadays, like GPT and so on and so forth, the main difference is that BERT is only this part, is the encoder part of the transformer. GPT is, implemented as the encoder. There are differences, like in particular, with the encoder, you cannot really generate text. With the decoder, you can generate text because the decoder is actually designed for text generation. The encoder-decoder architecture is also used in some of the more advanced, advanced large language models. But in particular, this architecture was initially proposed to do translation. So here you input a sequence of text in a language, and here you decode it in the other language. So why is this a breakthrough? Well, because now from this moment on, you were able to do the same things that computer vision guys were doing. That is training pre-training a model and then use it in downstream tasks. And if you measure the performance on the downstream tasks, you would see that they were really, really better than the state of the art. And the difference was just the introduction of this module producing contextual word embeddings. And in particular, this, the advent of BERT also introduced a revolution, if you want, in information retrieval and search. So as I said at the beginning, information retrieval was mostly done by relying on the inverted index for text and metric indexes for multimodal, multimodal objects. Now, thanks to BERT, first of all, you could train a, retriever in a very trivial way, provided you have, of course, we are doing machine learning, right? So provided that you have training data, but throughout the years, we collected and we accumulated a lot of training data. So in fact, we could immediately do it. The straightforward way to do, retrieval using BERT was to use a so-called cross encoder. That is, here sentence A could be, say, a query, sentence B could be a document, and then the classifier would return 0 or 1, or the probability of the document being relevant for the query, right? So so this worked beautifully. What's the problem? The problem is that you don't have an index, right? So you have to recompute the representation of the document. Of course, you have to compute the representation of the query, but the document was always the same. So you would have liked to have these representation pre-computed. Therefore, the alternative methodology was this bi-encoder, which is also straightforward. These are what is usually called in machine learning jargon a two-tower model. So you have the query going through this tower here, and you extract a representation, say U, and then the document going through this layer here, this tower here, and then you get the representation V, and then the similarity is given by the cosine similarity. So we are getting really, really close to the metric, the searching metric space community, right? Because now what you can do, you can pre-compute these V vectors for all of the documents in the collection, right? And once you have computed them, you just need to, compute the representation for the query and then search through, a data structure, which is nowadays called vector DBs, vector database, that returns the top case similar documents with respect to the representation of the query. So if you have if you have questions, feel free to to type it in the chat or interrupt me whenever you want. Okay, so therefore, this kind of started this, I would say, fight, because there are still people believing that inverted indexes are still better than dense vector retrieval, which, and by the way, there is a whole branch of, let's say, research, which is called neural IR, which is exactly this kind of things, like how to do IR mainly or only using neural, let's say, neural methodology. So instead of using an inverted index, you use bi-encoder and stuff like that. Actually, there is another, let's say, there is an evolution of neural IR, which is called generative IR. So instead of retrieving the doc IDs, you want to generate the doc IDs. It sounds like magic, but it actually works. And there is a whole branch of research. There is a whole lot of research papers and research opportunities that go in that direction. So why did I do this long introduction? Because I wanted to get you more or less on the same page on the fact that now you have, sorry, let me get back here, you have an architecture, a module, if you will. Let's say, let's focus here on this, but it's the same for the bi-encoder case. So a module that can be used, right, to retrieve results, right, to retrieve kind of results, but at the same time is differentiable. So why is this important? Why it's important that the whole architecture represents a function that can be differentiated? Because, training is done by gradient descent, gradient. So you have to be able to compute the gradient. But now there is another important thing. And that was actually exploited in this paper that started the whole RAG revolution. Again, this is an interesting paper in the sense, if you look at the set of authors, these were all sitting essentially, like, besides my chair when I was working at Facebook. Most of them are from Facebook AI. Alexandra Pictus is actually currently a third-year PhD student of mine. Fabio is a good friend of mine. All of them are good friends of mine. So Patrick is leading the RAG team at Cohere. Sebastian Riedel is part of the Gemini team at DeepMind. Dawi Kila has started a startup, guess what, on RAG that has raised more than $2 billion. So all of them, I mean, most of them have done very, very interesting things after that. I also want to give you a sort of a lesson in the sense, like in when you have to give a title to a paper, try to think of a title that is really catchy and people would read just by looking at the title. Meaning, before RAG, we actually come up with the idea of RAG. I mean, I know I sound like someone, like illuded or some lunatic, but you can check the paper. I mean, these neural databases has exactly, I mean, with different names, but has exactly the same structure of retrieval augmented generation. But at that time, retrieval augmented generation was really retrieval augmented generation. That is, they wanted to, let's say, do question answering or fact verification or whatever you want, question generation, whatever, by essentially end-to-end, let's say, produce the result. End-to-end means that also at training time, they were back propagating end-to-end also through the query encoder, which means you could, and this of course is extremely expensive in terms of training time, By the way, this was this is a paper at New Rips 2018 or 19, if I remember correctly. Anyway, so the real revolution now is that you can do, let's say, question answering using information retrieval as the initial part of the generation. So what's the difference here? The difference is that before this paper, well, actually also before the neural database paper, but let's say before this paper, generation was, let's call it closed book. That is, you didn't give to the LLM, to the generator, any information from where the correct, let's say, text to be generated was, let's say, inferable. So let me give an example. So suppose you say, who has been the, let's say, the best soccer player in the world? So without RAG, the idea is that the LLM produces the answer because somehow it has seen that during a training time. But of course, at training time, it has seen a lot of things. And for most of the questions that are long tail, let's say, so like rare topics, they couldn't actually do it. But instead, for rare topics, an information retrieval system is very, very good at it because, you know, it retrieves documents matching the query. So it doesn't really, I mean, the frequency with which documents were speaking about the topic is not an issue. It's not a limiting factor. So putting these things together, you could, let's say, firstly retrieve the documents that potentially contained the answer. And now, by conditioning the generation on the retrieved documents, you increase the quality of the generated answer. In particular, you guess correctly the answer to a question. And in fact, if you look at results, these are all question answering tasks. You can see that, let's say, RAG really, really improved all of these tasks, right? And also in classification scores, right? This is, let's say, SOTA, it's state of the art, but in fact is an oracle, because here, let's say, all of the generation classification were done by feeding the gold, let's say, evidence, the gold document. So it's like, look, you have to answer the query and you have to answer the question, and the answer is here, right? So this is an oracle. I mean, you cannot really beat it. And in fact, as you can see, all of those are below these numbers. But if you look at what RAG did, it increased all of it, let's say, either token or sequence. The difference is that in this case, you produce a token by token, and here you produce a sequence of text. But in all the cases, you beat the current baseline, which was BART, and you get really, really close to the oracle without knowing the goal, but just relying on retrieval. So, as I said, this was the original proposal that was done. But as you know, in many, many cases, you take this idea and you actually try to adapt to your use cases. Nowadays, when you speak about RAG, you think about the application, or let's say the methodology that I'm going to show right now. So RAG is, again, retrieval augmented generation. So it has the generation, let's say, part in it, right? So generation is done by an LLM, a large language model, okay? Typically a decoder-only transformer, so GPT or Llama or whatever. Now, what do? You feed a query to the LLM, like what is the color of Napoleon's horse, who is the CEO of Twitter, how old is Florin? Florin, by the way, is the main author of the Power of Noise paper that I'm going to show you in a second. And then, in this case, it's a closed book. so without retrieval, in a closed book environment, you rely on the LLM to retrieve the correct answer. So, for instance, in the case of Napoleon's horse, the answer is actually incorrect. This is what you usually call hallucination, right, in an LLM. Then maybe you can actually answer correctly, because this is maybe very popular. So the LLM has seen it many times, and it doesn't have any issue answering it. And then in this case, how old is Florin? Who is Florin? Okay, because the LLM doesn't know it. So this is hallucination. Okay, in this case is obsolete as well. Sorry, in the sense that now Elon Musk is not the CEO of Twitter anymore. Anyway, so let's see, how do we improve this situation? So you set up this kind of more complicated architecture. It's not really more complicated. So you start from the query and you add to the architecture an indexing phase, like you have in web search, right? So you're back to web search. And what do you index? You index chunks of the input document. So you do not index all of the documents. And indexing in this case, it's not even, let's say, associating terms with the ID. It's really building a vectorial representation of the chunk, of the piece of text. Now you end up with billions of these, millions of these, but you have efficient, let's say, retrieval mechanisms. I mean, like Edgar is an expert in these kind of things, and he would have, of course, came up with the idea of using vector databases. Now out there called, but like search indexes for metric spaces. So this is essentially the idea. So now the retriever, when the query is inputted to it, retrieves k chunks, in this case 3 chunks. So now in this case, Napoleon Bonaparte's horse Marengo was renowned for its striking gray color. Marengo named after a significant battle victory. Chunk 2, Josephine de Bornay, Napoleon's first wife, had a preference for horses with elegance. Her favorite was a chestnut-coated horse. So you see, these 2 chunks, of course, the correct answer is contained here, but these 2 chunks are related. So in a metric space, they are probably close together. So they are likely to be retrieved together in response to this query, right? And then, of course, usually you, let's say, order the chunks by the similarity with the query or query representations. And of course, as you move down to the list, let's say, the relativeness is lower. Like in this case, it's just a sentence about Napoleon Bonaparte and not about any horse. Now, the job is not over yet, because usually what you do in RAG, you feed both the query and the retrieved chunks to a prompt. So you build a prompt, right? So, and you say something like, answer the question based on the following information. So you put the context, which is a concatenation of these chunks, and then you formulate your question. What is the color of Napoleon's horse, okay? And then finally, you feed these to the LLM, and you're used to it, I guess, GPT, ChatGPT, or whatever, and then the answer is generated. So Napoleon's horse's color was gray. Okay, questions so far? Okay, if there are no questions, let me go. So let's now, after this introduction, I'm ready to actually present to you what we were curious about. My original research, let's say, area was information retrieval. And more often than not, people working on RAG were NLP guys, natural language processing guys. And it's well known that the information retrieval guys are better at doing retrieval. I mean, at least they believe so. And in fact, one question that we had in mind was, but are current retrievers, let's say, are current retrieving strategies ideal for retrieval augmented generation? Is it a problem that is worth being studied? So starting from that, we, let's say, came up with this paper that actually made a lot of noise in the Twitterverse. It was published at CICESE 2024. Well, let me also tell you a story. So reviews of this paper at CICESE came out very, very bad. Like only one weak accept and the other were like weak reject. Consider that on Twitter, this paper, I mean, we put it on archive and people discovered it, and it had more than 200,000, no, sorry, more than, yes, 200,000 views, more than 1,000 retweets, let's say lots of likes and so on and so forth. There are reading groups about this paper, even before CICESE. We have 50 citations, you know, from, I mean, already there, and, you know, and it's not a technology paper. It is, you don't see any new algorithm here. You only see an analysis of the retrieval effectiveness on RAG. So we called it the power of noise, and you'll see in a second why. Maybe also the name in this case was a good thing. And as you can see, this has been done in collaboration with, let's say, some of my students and postdocs. Florin is the leading PhD student, the leading author. And then you can see maybe names that are familiar to you, like Yoel Marek, that was at Yahoo, then, I mean, first Google, then Yahoo, and then Amazon, and now is at TII. TII, incidentally, is also the institute that has released one of the most famous LLMs, which is Falcon. Also, fun fact of the record, Yoel was the main scientist. So the main idea, the main person to, let's say, to come up with the idea of doing auto-completion in the search, you know, the search bar. So when you go to Google and you search something and you see the auto-completion and the, let's say, the list of, let's say, queries that you can auto-complete from here, that's actually Yoel. So, and again, why we're interested in that problem? Because we read, for instance, this kind of paper, like say this kind of article, say Google wants you to forget the 10 blue links. Like Google doesn't want you to, let's say, go through the list of results. It wants to give you the results. So we said, okay, if Google wants to kind of ditch the retrieval phase, or at least hide it, you know, in order to promote result generation, maybe we should really go look and see if retrieval is important. So our current retriever ideal for RAG. Meanwhile, like while we were doing, let's say, doing some experiments, this paper, Lost in the Middle, which is another very much celebrated paper, came out. What is this paper showing? This is showing a very surprising effect. So here on the y-axis, you have the accuracy of a RAG system. So how accurate the answer of a RAG system was, right? On queries with, let's say, okay, so when the prompt contained 20 retrieved documents, among these 20 retrieved documents, the golden document, so the document containing the answer, was placed in the prompt, but at different positions. So here, you see that the gold document is positioned first, but then the gold document here is positioned second. And as you can see, the accuracy drops considerably. Same when it's position third, and so on and so forth. And at some point, it goes below this red dotted line. This red dotted line is the performance of an LLM without retrieval. So without retrieval, so the closed book thing. So as you can see, at some point, depending on where you place your gold document, you are actually confusing the LLM more than if you didn't put any retrieved documents. Right? And then at some point, as you move let's say, beyond the middle point, the golden documents, accuracy, gets back, but never at the position, never at the level of the first one when it's closer. So let's say, again, are current retrievals ideal for RAG? Meaning, are they aware of this effect? So this was actually the motivating, let's say, question, but you'd see that we discovered maybe an even weirder, let's say, effect. All right, so let's see, what do we do? So first of all, we came up with a sort of a taxonomy of retrieved documents. So let's imagine you have retrieved these chunks. So Napoleon Bonaparte, so chunk 1, chunk 2, and chunk 50. And this is the query. What is the color of Napoleon's horse? So here you can see that this chunk here, chunk 1, actually contains the gold. It's actually the gold document. It contains the actual answer, so gray color. This one, instead, we called it distracting because if you see, it contains the right set of keywords, but you can infer, if you are not looking at it carefully enough, it might let you infer the wrong color. So I don't know who's a professor among of you, and if you have ever tried to trick your students, you do the same, right? You maybe in a multiple choice question, you put a possible answer that is very similar to the correct one, but some different things. So it's a distracting answer. And then you have random documents. That is, in this case, it's totally not about horses, not about Napoleon, and so on and so forth. All right? So what do you do with this? So first of all, you build a prompt. And now we build prompts by exactly and carefully placing gold, distracting, and random documents. So we start with the input or the instruction. So the instruction is shortly answer to the question, max 5 tokens, based on the following information: context, and then the question. All right? Consider that one of the things that you should always keep in mind is that it has been shown in the literature that if you want the RAG system to perform as better as possible, you should put the gold document as close as possible to the question. In this case, the gold document should be placed second. In chunk 2. So if you, let's say, pass, if you see, let's say, and if you do that, and you pass as context chunk 1 and chunk 2, this is a real example coming from experiments. You see that the RAG system says Napoleon's horse was chestnut colored. And we said, okay, this is interesting. Let's see if we can measure this kind of effect. So here we have the following thing. So the number of distracting documents, this is the symbol for distracting, is here. Each row corresponds to a different number. Far, mid, and near columns correspond to where you place the gold document. So far, you place the gold document as far away as possible from the query. Mid, you place some distracting, the gold, and some other distracting in the query. So this one was to kind of emulate and reproduce the problem with lost in the middle. And here, near, instead, you place distracting and then the gold document close to the query. First thing, of course, when you retrieve 0 distracting, so you basically always pass just the, let's say, just the golden document. Of course, all in these cases, there is no difference. You get to 0.56 accuracy. In this case, let me explain to you what accuracy is exact match. That is, you look if the answer is exactly matching the one that was in the test data set. So, for example, if you say, how tall is Fabrizio? And you say, Fabrizio is 5 feet tall instead of 5 feet, in that case, the answer is wrong. although the answer is correct. So this is a disclaimer, but this is the way, let's say, people are measuring the accuracy of RAG systems at least nowadays. As you can see here, we are using an LLM, which is Llama 2, but results are consistent with other LLMs. So let's see what happens when you add, let's say, multiple documents. Of course, here you can see that, okay, so this is the top, let's say, accuracy. So in any case, when you add distracting documents, you always lose accuracy. And in this case, if you put yourself in the worst possible condition, that is, you put yourself with the lost in the middle, let's say, case, and you retrieve many, many documents, the LLM is really lost. So the decrease is 68%. And even if you put it near, of course, you have a lower decrease, but the distracting elements, the distracting documents are still negatively affecting the results. And this is consistent through all the LLMs. So now we said, okay, is the content, let's say, is the content of the document that is distracting and that is actually affecting the results, or it's the fact that we are adding documents that are not containing the golden or the actual answer? So how do you measure that? Well, you measure that by adding really random documents, right? So let's see what happens. So this is the same case, except we do not have distracting, we have random. So like the ones that are really far away from the query. And as you can see, we are already observing an interesting phenomenon. That is, yes, we are decreasing the accuracy, but not as much as before. So something weird is going on. So remember, before it was 66%, and this is 47, 46. But now the real magic happened. Now you place the gold document close to the query, you add random document, and bam, you have an increase of 2.2%, or 3.85% in accuracy. And this was really, really weird for us, right? You are essentially adding random documents and you increase the quality of the results. How come? So again, as you can see, we try to measure, let's say, the attention distribution in transformers. Here on the y-axis, you can see the attention layers, so the number of layers in the transformer. And each document in the prompt has a different columns. As you can see, when you have a distracting document, the attention is also placed to this document here. So the generation, let's say, place the attention to these two documents, and of course, sometimes it gets it gets confused. Instead, when you do not use any distracting document, but just random, the LLM can immediately recognize that the answer should be contained in the goal, right? Okay. Now, let's see another interesting document. So imagine you have, let's say, 10, let's say, retrieved documents by an information retrieval system. It's called Contriver. It's a dense retrieval system. So you retrieve 1, 2, 3, 4, up to 10 documents, and then you insert, let's say, on purpose, random documents. Okay? So here we do not have any gold documents. It's just information retrieval plus the addition of random documents. So as you can see here, the increase is even higher. In the case when you retrieve 4 documents and you add up to, or actually 15 random documents, right? So remember, the context is 20 documents. So when you add 15 documents, you increase the, let's say, the accuracy by 35%, which is a huge number. So we try to answer to this, are current retrievers ideal for RAG? And maybe not. So we are really calling here for, let's say, IR researchers to try and come up with a better way of doing IR for RAG. Okay, so IR is kind of living a second infancy. The first infancy was web search. So as you can see, we have, let's say, we have shown these relevant insights. So relevant documents should be placed near the query. This was known. Distracting documents are extremely harmful, right? And random documents instead are very, very useful. By the way, I didn't tell you, but we also have experiments in the paper that you can access if you go to this QR code reference. You can actually also build really random documents. That is, you can randomly sample tokens, right? And that's a chunk. And even if you do that, you still experience a 35% increase, or in that ballpark, increase of accuracy. So it's a very, 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 let's say, interesting results. Now, if you have questions on this part, because now I'm moving very, very quickly to a very recent one, but let me know. Otherwise, you can ask questions at the end. I'm moving very fast towards the end to get some questions if you want. So, there is a question. Okay, at the end. Okay, sure, Edgar. So now another interesting question that you might want to ask is the following: base versus instruct. I don't know if you know, but LLMs, when you access and use an LLM, you can see always the suffix base or the suffix instruct. So the difference is that in the case of instruct, the LLM has been fine-tuned to actually follow instructions. So like ChatGPT, for instance, is an instruct LLM because it follows instruction, okay? If you do not, and if you have followed the whole, let's say, fuss about ChatGPT, you know that it has been fine-tuned using reinforcement learning from human feedback and blah, blah. So essentially, the LLM is fine-tuned to follow instructions. So again, we were kind of curious to understand whether instructs are always used in RAG systems, okay? We were curious to see, but what happens if you actually use a base document, a base LLM in a RAG system? No one has ever tried to do that. So we took Llama 2, 7 billion, and Llama 2, 7 billion is actually, if you look at the instructions, it's not a pun, but if you look at the instruction, they ask you to use a template when you want to follow an instruction. So you have to explicitly say that you are actually giving an instruction, okay? And anyway, so there are these cases, no templates or no or template. And also, one of the things that we added is the following: if you build a prompt with some chunks, we explicitly asked the RAG, the LLM, to say no less if the chunks, didn't contain the answer. So we tried to force the LLM to not use the internal memory. So you have these kind of things. Let me show to you. Let me go straight to the, let's say, to the surprising results. So the surprising results is that despite what people were believing, so despite the fact that you're actually asking and giving an instruction when you build the prompt after the retrieval part has been done, the base model that are, let's say, here without, you see, the I, are actually performing better than the instruct ones in natural questions and trivia question answer. And this is consistent across the board. That is also true if you increase the number of retrieved documents. The instruct ones are returning, let's say, returning incorrect results, and the base one are actually better. And the same, let's say, in another setting, I mean, this is similar, but as you can see, also in this case, the instruct ones, in this context, when you actually include the template, the instruct ones perform better. Now, we try to understand if, for instance, the problem was that that the instruct models were explicitly, let's say, instructed to not reply unless they were 100% sure. And this is indeed the case. So here, as you can see, the rejection rate, so meaning, sorry, the recall from parametric memory, which is the equivalent to closed book, essentially. So we want to understand if the, let's say, the answer that was given was actually retrieved from the transformer model. So essentially, what we really want, we want this recall to be as low as possible, right? And as you can see, in this case, the instruction-tuned models are correctly exploiting only the prompt. The base models, which are these blue lines, are extremely, let's say, less likely to return nor s, even if the incorrect result is contained, even if no correct result is contained in the prompt. So what does it mean? It means that a base model tries at its best to answer the query. Is this a good thing? Is this a bad thing? I don't know. It's still an open question. And here, essentially, are the key insights of this part. So fine-tuning LLMs are sorry, I don't know what I wrote, but it's completely nonsense. I think something got canceled. Essentially, what I mean is that fine-tuning an LLM is not always better, but is more, let's say, trustworthy. That is, if this set of results is not containing the correct answer, it says that it doesn't know. Nor s is seldom returned by base models, again, because it tries to retrieve the right answer from its memory, even if you don't give it in the prompt. And let's say, in general, it looks like, and this is a generic comment, it looks like supervised fine-tuning and alignment detrimentally impact the model's capabilities for retrieval augmented generation systems. This is it. This is essentially what I wanted to show to you. These two results. One is very new, which is the last one that I showed you. One is a little bit more known, but in general, I hope I kind of I've been giving you some interesting, food for thought. And thank you for following.
Okay, I think we can start now with the Q&A session, right?
Yeah.
Okay, very well. Professor Edgar, you have a question?
Yes. Okay. It has to do with what we discussed last time.
Okay.
Okay. In practice, removing the distracting documents is not feasible, right? Because you don't.
Exactly.
Okay.
That's correct.
Yeah. So the using the graph, the HSP is a way of removing distracting documents.
Yeah, let me actually also, let's say, give a little bit of a little piece of additional information. So while what you say is totally true, it is also true that you could boost a little bit more. So traditional IR or neural IR systems are trained in a way that it says, okay, is this document relevant or not relevant? So in a way, there is this dichotomy, right? That says, okay, this is relevant and you should return it, right? And relevance, most of the cases, corresponds to similarity. But as we showed here, relevance should also be aware of the similarity, meaning if something is very similar in the, let's say, vector space of chunks, but is not labeled as relevant, maybe the, let's say, the retriever should actually learn this. But I mean, it's a very tough, task, but also this is something that has never been done. So like no IR, let's say, phases have been trained with the distracting concept in mind. But you're right, using an appropriate, let's say, as you said, like diversifying more should actually help. This is an additional way of actually avoiding retrieving similar documents, but detrimental documents.
Okay, so probably should be a module in Contriver, not
yes, yes.
here. Okay,
not here. Yeah.
Right.
Yes, it's a retrieve. So again, surprisingly, the retriever is not up to speed with the generator, essentially. So LLMs are much better now than neural IR systems for RAG, of course, always keeping in mind RAG.
Thank you.
You're welcome. Other questions?
Yes, I have one question.
Sure.
How do you see the role of LLMs evolving in the context of RAG as these models become more like sophisticated?
Sure.
Will we need less retrieval, or will retrieval become more important as the models grow?
So I believe that retrieval will become more important. In my opinion, we will observe, maybe some of us will do it, we will observe, let's say, an evolution of retrieval, meaning you do not retrieve chunks, but maybe you retrieve vectors directly, and then you generate answers from so instead of placing the text in the prompt, you just condition the generation to some vectors. This has not been done yet. And what would be here the benefit of doing that? It would be the fact that, again, you will go back to the end-to-end training, right? So because now you are essentially taking the vectors retrieved or generated by the retriever, and then you pass it to the LLM, and then you back propagate the error down to the retrieval part. So I believe that retrieval will be a very prominent problem in RAG. But also another thing is that, in my opinion, also LLMs will have to be aware that are used in a RAG system. And in particular, what I mean here is that probably the attention mechanism that is used in nowadays LLMs, like typically grouped attention, flash attention, stuff like that, are not suitable for RAG. I mean, the lost in the middle thing, the fact that if we pass some distracting documents, the quality decreases, it shouldn't be there, right? If I give you, if I give you the gold document, I mean, in the majority of the cases, unless you are really, let's say, not looking carefully at the documents, in the majority of the cases will help you. I mean, you will not get distracted. So there must be something there going on that should be fixed in LLMs as well. So again, I believe that RAG is just the beginning of it. And in the following years, I don't know, months for sure, but even years, we will see lots of interesting, let's say, findings published and proposed.
Okay, thank you very much. We would like to express our sincere appreciation to Professor Fabrizio Silvestri for his insightful and engaging presentation today. It has been a privilege to learn from your expertise and the valuable research you shared with us. On behalf of the Computer Science Department at CICESE, we would like to present you a diploma. Give me a second, I will share it with you. So, el Centro de Investigación Científica y de Educación Superior de Ensenada otorga el presente reconocimiento a Fabrizio Silvestri por impartir el seminario on Retrieval Augmented Generation and Some Unexpected Effects. y pues con la firma del doctor Pedro Gilberto López Mariscal, coordinador de posgrado en Ciencias de la Computación. La fecha es 6 de septiembre del 2024. So thank you very much for your presentation. It was a unique experience and we hope to see you again someday.
Thank you very much. Gracias,
Yeah.
muchas gracias.